Hello, my name is Fire Charles. Today I will be present task number 1 of our group assessment 2 for Big Data Unit. Our team completed 3 tasks. Of task 1, nearest neighbor search, which I completed. Task 2, skyline search, will be presented by Nimorshih. And the last task, number 3, the final report will be presented by Ratna Dage. Okay, so let's start my task number 1, nearest neighbor search. Here is agenda for task 1. First of all, I'm gonna explain how the program works and share some comparison between the 3 algorithms which I used. And the main parts of task 1 is program analysis and results. It means the explanation and analyzing of coding. Finally, I will share some reflection and learning from the task 1. Here's the slide to explain how the program works. The program finds the nearest parking location from a big data set for given 200 query points. The program data set structure is two-dimensional, 2D, of its latitude and longitude values and ID of each location. Also, I implemented 3 algorithms: sequential, R-tree-BAP, and divide-conquer. Next slide, I will explain more detail for each algorithms. Then outputs from all algorithms, I save it in single txt file as named as task 1 output. Before starting my analyzing, I just want to share a small comparison between the algorithm. As shown here, sequential scan is slow because it checks every point. Branch and bound uses an R-tree to skip far away areas. Above the divide conquer, it splits the dataset into smaller parts for faster search, so it built 2 R-tree for each part. So as we know, which one is faster and slow and why. Okay, now it's time to analyze my program. Here is a main structure of coding that will starting from helping functions to main executions from the program of task 1. As I shown image of coding for each part on right side. So it's a helping function. The program starts with 2 helpful functions. First one is Euclidean. Before I mentioned Euclidean, it computes the straight line distance between each 2 points using the Euclidean formula. Also, it uses it repeatedly to find which data points is close to query points. Second helper function is reading function. Reading point file, it can help to read dataset and query files. If there is some invalid or empty lines, it will skip. So it don't stop the program. After result of the reading, it returns a list of tuples ID, X, and Y. Generally, this helping function is preferred data set for a clean structure for further processing. Then I define the class for R-tree. The 2 classes build the R-tree structure, MBR and R-tree node. MBR, minimum bounding rectangle, it surrounds nearby points and can estimate the shortest distance from query to a rectangle. R-tree node defines each node, either a leaf with points or an internal road with a child rectangles. So I learned from the unit that the construction algorithm of the R-tree is to aim the minimizing the perimeter of the sum of all MBRs, and all area of the MBRs rectangles should as small. So that algorithm is working behind these functions. Then it's time to build R-tree using bulk route. This function creates a full R-tree. It sorts the dataset, groups nearby points, builds leaf nodes, and keeps merging them until a single root node. As a bulk loading avoids inserting one point at a time, it's a balanced tree in one piece, so it can faster and more suitable for big data case. Then search R-tree with the branch and bound. I call it BAB. R-tree nearest function performs the search. It starts from the root node and uses priority queue to visit. Then if a rectangle is already farther than the current best distance, that branch is skipped. It's a main approach. This pruning avoids thousands of distance checks, making the search much faster than sequential scan. Now it's time to split dataset for divide and conquer approach. Split the function prefers data for divide and conquer. It sorts points by the x coordinate and split them into two smaller parts. Each half can be processed independently, which helps scale a larger datasets. It reduces R-tree depth and allows partial parallelism, and each R-tree handles a smaller region, so it improves performance and accuracy much more. Now it's finding a nearest neighbor algorithms. Now it means now all components come together. Sequential NNCH function checks every data point for each query and keeps the closest. Also, it always correct, but we know it's a slow. This approach is slow. And second BAB, it's a nearest neighbor search using R-tree structure. It's a much faster because it prunes irrelevant areas. Last one is BAB divide conquer search. This function is split the dataset into two parts, build two R-trees, search board, and takes the closer results. Now I'm using main function. This function ties everything together. It means it reads the files, runs all three algorithms, and writes the outputs from the algorithms to output files. It also prints runtime summaries on the screen for each algorithm output. From the result, we know that sequential scan was the slowest because it checks every point. Brand and bound R-tree was the fastest, and the main important thing was pruning method for this approach. And finally, divide and conquer was close behind, but takes extra time because it's built two R-trees. So it's time to share my reflection and learning from this task. Number one, I learned how spatial indexing optimizes nearest neighbor queries and understood how branch and boundary reduce unnecessary competition. Also, I demonstrated performance trade-offs between simplicity and efficiency. Also, they have some practical takeaways. R-trees are essential for large spatial datasets like parking location, which I used on my task number one. Thanks for listening for my tasks. Now it's time to hand over my partner, Niam Arsha. Thank you.
Hello everyone, my name is Nem. Today I'm going to present our group's implementation of task to Scala and search from the assignment to big data. So we are our members are negotiated and allocated with task 2. So let me share first the screen. The main purpose of the task 2 is identify the ideal homes with lowest total cost and lowest price using three skyline algorithm. And the data set is the very large amount of the data based on two criteria. First is total cost of the home and low price of this per square meter. The ideal home should have both a low cost and low price. So we must remove the homes are dominated, meaning another home is better for both attribute to find optional points. We implemented three algorithms. First is sequential skyline. Second is branch bound skyline using R3. And third is divide and conquer with branch bound skyline. So data set is we choose the city3 file because of our student's ID last digit number. So dataset contains 300,000. It is a large amount of the dataset. So efficiency, computation time is the more important. So we use it like R3 and the branch bound skyline to reduce computation time. So following the program code we implemented. First is point class, and second the node class, and thirdly it is R3, and also minHIF. So the purpose of the point class is to store each home's ID and cost and price per square meter. And node class is to represent a node in the R3 with children and a minimum bounding rectangle. So an R3 class handles both loading and node splitting and tree construction. We also implemented a small minHIF class to serve the priority queues for the branch bound skyline algorithm. So first algorithm sequential skyline. So this one it is to the each rows is divided to the ID and the X axis is the total price of the home and Y axis is the per square meter. So sequential skyline first algorithm is the simple one. We compare each every pair of the point to see if one is dominated another. It belongs to if it's not dominated by another, it belongs to the skyline. So R3 plus branch bound skyline that we build an R3 to organize points. Each node's minimum bound rectangle summarize the group of the homes. And the branch bound skyline algorithm use minHIF to explore the most promising node first. Thus close to the origin, low cost and low price per square meter. Dominated minimum bounding rectangles are pruned early, so we avoid checking most of the dataset. So this reduces complexity and achieves nearest local linear performance. So the wide and the third algorithm, the wide and congruent branch bound skyline algorithm. So we split dataset based on the median X value and Y value. The bool QR3 and run the branch bound skyline for each dataset, and then merge the two partial skyline by filtering out the dominated points. So this is our result and performance. First, the sequential skyline 1.8 second and 15 points. And secondly, branch-bound skyline with R3 it is 0.003 points. And divide and conquer branch-bound skyline is 0.5 second 15 points. So all three methods return the same results, same set of the skyline points. For example, ID number and cost of the home and price of the per square meter. And this presents most effective homes in the datasets. So dataset, the result shows that the R3 is the best method, is the best efficient and suitable for the large dataset, and the divide and conquer algorithm is the better for parallel and distributed environment. So in conclusion, our group successfully implemented and tested Scala and three-scala search algorithm entirely. So we follow with our the class workshop approach and ensuring academic integrity and the meeting following meeting to marking criteria. Throughout the task, we learned how data structure like R3 and heap based on search can reduce the computational complexity. This experience helped us to understand how Scala and queries are used in real-world applications such as real estate and recommendation system and multimedia decision making. So let me share let me run my code. So I will save my file in the desktop. So our code is successfully run and the results are here. So this data set that's 33 and sequential skyline with 15 points and 2 seconds execution time. And second task is branch-bound skyline R3 it is 0.002 seconds, 15 same result with the sequential skyline. And also task rate divide and conquer branch-bound skyline is almost half second, same as task 1 and task 2. So thanks to listen me.
Hello everyone, I am Artna Degi. Today I will present two tasks. The objective of these two tasks is to perform efficient special queries using R-trees and advanced techniques based on techniques such as branch and bound skyline based on nearest neighbor search and skyline search. I built the R3 for 10 special points and one query point at 10.6 and applied branch and bound algorithms. In task 2, R3 for 15 special points is built and applied BBS skyline algorithm. For both the tasks, such as nearest neighbor search and skyline search, we use divide and conquer version to demonstrate improved pruning and reduced search costs. The main concepts covered are artery construction, overflow handling, BAB-NN search, BBS skyline search, and divide and conquer with algorithms. Let's move on to next slides. It's about core implementation constraints. I intentionally set the R3 node capacity M equal 3 and minimum is 2 to trigger overflow and split events. As required, no external R3 libraries were used. It was implemented manually. Lastly, Euclidean distance is used and the priority queue-based traversal. In terms of R3 construction algorithm, I built the R3 using the classic algorithm. As you can see, there is a R3 structures I included. Firstly, choose leaf. Descend to the leaf required minimum bounding box enlargement. Secondly, insert the point and update the bounding box. Thirdly, if capacity exceeds 3, perform a linear split using far apart seeds and then assign entries based on list area enlargement. In this image, I try to show overflow and then split it. Lastly, update MBRs upward. This makes splits and tree structure easy to observe and supports efficient query traversal. Let's go to the BAB nearest neighbor. This objective is find nearest point in 10-point dataset and query point is 7, 6. In this algorithm, I maintain a priority queue keyed by the lower bound distance to each MBR. When we pop up the first point, we record its distance as D star and prune any nodes whose lower bound is larger. This guarantees correctness and reduces expansions. The final nearest neighbor point to the query 7.6 is P7. At the distance is approximately 2.24. You can see from this picture. In terms of divide and conquer, to optimize further, I divide the space at x equal 5. I built 2 smaller arteries and search this site containing the query first. When we compare D star with the distance to split line, if the split distance is more or equal D stars, we skip the other side. In this experiment, I still find P7, but I prune the left 3 earlier, demonstrating efficiency gain. Let's move to another slide. It's about BBS algorithm with the skyline search. In this task, we compute the skyline using the BBS algorithm. A prioritizing queue is used again, but instead of distance, prioritizing MBRs with promising lower bound coordinates. When I encounter a point, if no skyline point dominates it, I include it in the skyline and prune dominated nodes. This efficiently outputs the skyline without scanning all points. Lastly, in this divide and conquer with branch and bound search, we run this algorithm on each side and merge partial skylines. This reduces dominance checks and improves runtime. Overall, R-trees and priority-driven exploration allow efficient nearest neighbor and skyline queries with strong pruning ability. Thank you for your attention.